In this skill, we're going to be finding the pH of a solution when we mix together an acid and a base. This time we're going to have one weak and one strong, and there's going to be an excess of the strong one. And this skill is going to work exactly the same as the previous ones. The calculations are going to look identical. So let's start by figuring out what we have to start with. We're told we mix 1.3 liters of a 0.07 molar perchloric acid solution with 1 liter of a 0.05 molar methylamine solution at 25 degrees C. Again, we're given the molecular equation showing the full formulas of our reactants and our product. We're also given the net ionic equation, which removes any spectator ions. We can see that because methylamine is a weak base, we see it in full in the net ionic equation, whereas because perchloric acid is a strong acid, it's been split up into its ions, and the participator ion, which was the ClO4 ion, has been removed from the equation. Okay, let's start out by figuring how many moles of each reactant are present. Let's head to the reference sheet. Here's the solutions page on our equation sheet. Here's the molarity equation. Molarity equals the number of moles divided by the volume. Molarity equals the number of moles divided by the volume. We're trying to calculate the number of moles here, so let's multiply by V on both sides and cancel the V's on the right. That gives us the number of moles is equal to the volume times the molarity. So let's do that here. For HClO4, our volume is 1.30 liters and our molarity is 0.0700 molar. If we multiply those together, we get a number of moles of 0.0910 moles of HClO4. For the methylamine, we have a volume of 1.00 liters and a molarity of 0.0500 molar. When we multiply those together, we get a number of moles of 0.0500 moles of CH3NH2. So let's go ahead and fill those numbers in here. Awesome, okay, so we've got a number of moles of each. Next, we need to figure out which is the limiting reactant and which is the excess reactant. So we're going to start by looking at our molecular equation and figuring out the ratio between them. In this equation, we have 1 mole of HClO4 reacting with 1 mole of CH3NH2. So we have a 1-to-1 ratio here. So that makes finding the limiting or excess reactant really easy. Whichever we have more of is going to be our excess reactant. So in this question, since we have 0.091 moles of perchloric acid, which is more than the 0.05 moles of methylamine that we have, we know that perchloric acid is the excess reactant. So we can fill that in here. Our excess reactant is perchloric acid. Our limiting reactant is methylamine. Because the excess reactant is an acid, our solution is going to be acidic in the end. Now, our goal is to find the pH of the solution, so we're going to need to know the concentration of H+ ions in our solution. So let's start by figuring out how many moles of the excess reactant remain at the end. We had 0.091 moles, but we know that 0.05 moles of that is going to react with the methylamine. So that leaves us with 0.041 moles of our perchloric acid. So we can fill that in here. So how many moles of H+ or OH- ions remain? Well, we have H+ ions here since we've got an acid, and HClO4 just has one H in it. So that means that for every mole of HClO4, we get 1 mole of H+ ions produced. So it's going to be the same as the concentration of HClO4. It's just going to be 0.041 moles of H+ ions. If instead it was H2ClO4, this would be twice as many moles of H+ ions. Okay, next we need to figure out our concentration. So we've got the number of moles, now we need to find the volume. The total volume of the solution is going to be the sum of the volumes of the solutions we mixed together at the beginning. So we had 1.3 litres of our acid, and we had 1 litre of our base. So when we add that together, we get 2.30 litres for the total volume of the solution. Finally, to calculate the concentration, we're going to use the same equation we used before, which is our molarity equation. Molarity is equal to number of moles divided by volume. Our number of moles we just calculated was 0.041. Our volume we just calculated was 2.30. So if we put those into our calculator, we're going to get out a molarity of 0.0178 molar concentration of H+ ions. We can fill that in here. Awesome. Okay, now we know the concentration of H+ ions. We're trying to find the pH. So let's head to our reference sheet. Here is the acids and bases page of our reference sheet, and here's our pH equation. pH equals the negative log of the concentration of H+ ions. So pH equals negative log the concentration of H+ ions. So pH is equal to negative log. We just calculated the concentration of H+ ions is 0.0178 molar. So if we put that into our calculator, we're going to get a pH of 1.75. So we can go ahead and fill that in down here. Awesome. So you can see this question functionally worked identically to the previous question where we had a strong acid and a strong base. In this question, we have one strong and one weak, but the one that's in excess is always going to be the strong one. So we calculate the pH or pOH at the end in exactly the same way as if they were both strong. We started by figuring out how many moles of each reactant are present and used that to figure out which is our excess reactant. If the excess is an acid, it's going to be an acidic solution overall. If the excess is a base, it's going to be a basic solution overall. Finally, to find the pH of the solution in the end, we need to figure out how much of our excess reactant remained, and therefore how much excess H+ or OH- ions remained. We're going to then add up our initial volumes of our solutions that we mixed together to get the total volume of the solution, and use that to figure out the concentration of excess H+ or OH- ions in the end. Finally, we'll use those in either the pH or the pOH equation to figure out our final pH. It's important to note that because we had a weak base, we have this ion formed that actually is a acidic ion. So this was our weak base, and this is the conjugate acid of a weak base. And the conjugate acid of a weak base is an acidic ion, meaning that when it's in water, it's going to react with the water partially to form some of our weak base again. So because of that weak base forming that weak conjugate acid, we do actually have a slight adjustment to this pH that we found in the end. However, because that was a strong acid that was in excess, and we're just talking about a weak conjugate acid here, it's not actually going to make a big enough effect to change our number. So we just ignored that when we did our calculations, since we know that our strong acid that's in excess is way stronger than the weak conjugate acid we have in our solution at the end, and therefore we know it's not really going to make much difference.